I now have the pleasure of introducing an architect, writer, and one of the key thinkers on biomimicry, Michael Pawlyn. Michael established exploration architecture in 2007 and has built a reputation as a thought leader in regenerative design and the circular economy. Michael is going to talk to us about biomimicry as an integral part of regenerative design thinking. Architect Michael Pawlyn.
Well, hello, and thank you very much for involving me. So it's great to be part of this design and ecology session. And I'm going to be talking about why I think sources of biologically inspired design are going to be essential to making the shift from a sustainable mindset to a regenerative one. And before I go any further, I just want to credit my co-author, Sarah. So Sarah and I wrote this book together, and quite a lot of what I'm going to be talking about comes from this book. So equal credit to Sarah for those ideas. Now, this diagram from Bill Reed, I think is a really useful description of the difference between a sustainability paradigm and a regenerative one. So this shows different levels of achievement in environmentally responsible design. The most basic level you could call conventional practice, or one step better than breaking the law. Above that is the realm of green design, of relative improvement, and that's where a lot of schemes that use LEED and BREEAM are. And then above that is fully sustainable, or as Bill McDonough has called it, 100% less bad. Now, the problem is that most of what we've been doing over the last 20 to 30 years in sustainability is below that line of neutrality. And that means that it's just part of a downward degenerative cycle. And I found this quite painful to accept, really. You know, I thought all that time I've been working in sustainability for 30 years, and I thought all that time I was making things better. And actually, a lot of that time I was just making things a bit less bad. And it's becoming increasingly clear that less bad is not good enough. And what we really need to do is to get above that line of neutrality into the realm of net positive. And just as we had a really lively debate 20 years ago about what the ultimate in sustainability means, now I think we need to be debating what is the ultimate in regenerative design. And my view is that biomimicry and biologically inspired design approaches are going to be a big part of how we will get to that ultimate stage of humans participating as nature and co-evolving as the whole system. And Sarah and I argued in our book that there are really three key differences between sustainable and regenerative. One I've already mentioned, is moving from less bad to net positive. Sustainability also tended to be very anthropocentric. It was just about humans. So we need to broaden that to a whole planetary perspective. And thirdly, sustainability tended towards being rather mechanistic, just focusing on a limited number of metrics. And we need to adopt a much more systemic approach than that. So I'm going to present what I think this means in terms of regenerative materials, regenerative buildings, regenerative cities, and then finally, regenerative landscapes. So starting with regenerative materials, this is the coccolithophore. So this is a marine microorganism. And according to Gaia theory, which was put forward by James Lovelock and Lynn Margulis, these were part of the regulating system of carbon dioxide levels in the atmosphere on planet Earth. So historically, in geological history that is, when there were increases in levels of CO2 in the atmosphere, you would have had massive blooms of these microscopic organisms growing these beautiful skeletons out of calcium carbonate, falling to the ocean floor and building up as layers of limestone, transferring carbon from the atmosphere via the sea into the rock and maintaining that balance. So there's a very good case for saying that we should be making more stuff from atmospheric carbon. Timber is an obvious example. I'll mention a few others shortly. And I think it's also important to appreciate that because planet Earth has evolved to become a very complex system, some would say a self-regulating system, that there's a lot that we can learn from the way that planet Earth functions to help us make this shift from sustainable to regenerative. So as one example, nature makes 96% of all living matter from just 4 elements: carbon, nitrogen, hydrogen, and oxygen. And of the remaining 4%, nearly all of that is just 7 elements. So biology uses a limited and safe subset of the periodic table and assembles those in very ingenious ways. And so you can see that rather than making materials that emit huge amounts of CO2, as we do when we make concrete, the closest equivalent in biology to concrete is coral. It's a large mineral structure, and it grows by taking carbon out of its immediate environment. And really, there ought to be a lot of research going into geomineralization and biomineralization, so that when we make buildings, we would be delivering a net positive by actually taking carbon out of the atmosphere. I think there's also a very big part for biological raw materials. So this is a material called, it's a high-performance insulation made by a company called Biome Limited. And this is just made out of plant fiber, agricultural waste, added to mycelium, and it grows into this very high-performance, completely non-toxic, fireproof insulation. So we can also learn from nature how to assemble those materials in very ingenious ways. This is a marine mollusk. It's got an abalone. And if you look at that under a powerful microscope, you see that it's made up out of these layers of calcium carbonate. And those are connected together with a flexible protein. At a chemical level, it's almost identical to ordinary blackboard chalk. But because of that microstructure, it achieves 3,000 times the toughness. And here's a house that my office designed based on some of these ideas. So it uses curves to create a stiff shape. And then it uses this idea of layered tiles, very similar to the abalone, to make a structure that is as thin as eggshells in relative scale terms. And we're pretty confident this house would use less than half the amount of material of a conventional approach. This is a table that my colleagues and I designed for an exhibition. So this uses a biologically derived polymer, so partly atmospheric carbon that's made that, and it uses that to 3D print a table that is designed using principles from bone and tree growth patterns. So this is based on biology in two senses. It's a biologically derived material and a biologically derived form, striving to get to the kind of levels of structural efficiency that you find in biology. So now moving on to regenerative buildings. This is a scheme that we worked on for a client in India. It's a zero-waste textiles factory. And as I'm sure lots of you know, textiles is an incredibly energy-intensive and water-intensive industry. Our client wanted to create a new model for industrial buildings in India. So we conceived of the building as having three main realms. There was the water cycle, the energy cycle, and then the factory itself. Within the factory, there are lots of different processes and machines that have different resource flows. And by looking at each of those resource flows and seeing how we could make use of underutilized resources, such as waste heat, we achieved really significant improvements in efficiency. The big breakthrough came from shifting from fossil fuels to biomass. So now we were getting heat and power. We were able to make use of a lot of the waste heat from the factory. And then for the water cycle, we worked with a biologist, a chemist, and a water expert to design out all the normal toxins that are used in a factory process like this. And by doing that, we were then able to use biological forms of water treatment that allowed us to get very close to closed loop on water. And down the middle there, between the two factory units, that's actually the water treatment system. So it uses plants and microorganisms to treat the water, and also provides a useful visual amenity. So the building in the middle, that's the staff canteen. So at least 3 times a day, the staff can get out of the working environment and get a connection to nature. And this is another really important aspect of biologically inspired design, biophilia. I'm sure a lot of you are familiar with this. And there are some great examples of hospitals that have used biophilia to achieve really impressive improvements in people's recovery rates. So people can recover as much as 8% more quickly and with half the amount of pain-relieving drugs when they're in an environment with a close contact with nature. This is another building we designed using biomimicry. So this was an office building. And we looked at maybe nearly 100 different biological organisms, helping us to rethink all the common functional challenges of office design, the structure, the daylighting, the ventilation, the fire protection, and so on. And we managed to make some really significant breakthroughs in resource efficiency. Moving on to regenerative cities now, the most persuasive model that I've heard, and Sarah and I write about this in our book, Flourish, comes from a group in the US called Biomimicry 3.8. And what they argue is that the way we design cities at the moment doesn't go anywhere near far enough. And what we should do is we should start by analyzing how a pristine, mature ecosystem in that part of the world would function. How much carbon would it sequester? How much water would it filter? How much oxygen would it produce? How much wildlife would it accommodate? A whole range of ecological performance criteria. And those should become the metrics for our new piece of city. We're nowhere near that at the moment with tools like LEED and BREEAM, but there are sufficient examples of elements of this that have been built that make me confident that this is perfectly achievable. So I think we're going to see more and more buildings that incorporate vegetation. I'm not completely convinced by the idea of putting trees on tall buildings, but I do think there's a good case for incorporating more vegetation to create habitats and psychological benefits. And we also need to find a way of doing this without increasing the embodied carbon of the building. So probably using more in the way of timber framed buildings. One of the biggest differences I think we'll see in a regenerative city is in the spaces between buildings. So this is a fantastic example in South Korea, in Seoul, the capital, where the mayor persuaded people to tear down a 6-lane motorway that used to cover this river. And they restored it and created this linear park, which has become a really well-used and popular amenity within the city, even contributing to significantly lower temperatures in summer in this part of the urban area. Another crucial discipline that we need to use in cities is the idea of biomimicry and ecosystems models. So what I mean by this is conceiving of a city or maybe a set of industrial processes as being the equivalent of an ecosystem where each of those elements is equivalent to a species with its resource flows. And just as in a real ecosystem, where the waste from one part of the system becomes the input or nutrient for something else in that system, that's what we need to move towards. Bringing cycles of food, energy, water, and waste together so that we can achieve major breakthroughs in resource efficiency, finding synergies between all of these different things. Now moving on to regenerative landscapes. This is a project that I jointly initiated quite some time ago. And what we were trying to do here really was to address multiple challenges simultaneously by using clever integrated solutions. And the kind of things I'm referring to here are challenges such as food shortages, water shortages, desertification, climate change. And we were looking particularly at arid parts of the world, and we were quite struck that a lot of the world's deserts were actually vegetated a fairly short time ago. So for instance, when Julius Caesar arrived in North Africa, what he found was this wooded landscape of cedar trees and cypress trees. His armies set about clearing those and created an intensive farm, which supplied the Roman Empire with about 500,000 tons of grain a year for a certain amount of time. But after about 100 to 150 years, they had substantially trashed that landscape. Previously, it was quite abundant and it had plentiful rainfall. When they'd finished with their very extractive model of land use, it had become a desert. So could we perhaps intervene at some of the edges of those deserts in a way that would generate renewable energy and produce food and revegetate deserts in ingenious ways? So this was the first visualization we created. And there are three core technologies here. There's forms of solar energy. There's a type of greenhouse that is cooled and humidified with seawater. And then there's desert revegetation. And what we found was that those three have some very interesting synergies between them. They actually work better together than they do individually. We built a version of this in Qatar, and this was opened during the climate change talks in 2012. And we managed to produce crops with half the amount of fresh water throughout the summer months, half the amount of fresh water compared to conventional approaches. And we really pushed this idea of ecosystems models. So the green icons are the various different technologies. And in simple terms, what we were doing is we were using what we have a lot of, sunlight, seawater, and carbon dioxide, to produce more of what we need. And these are all the interconnections between those elements. And I know that looks complicated, but I believe this is the kind of complexity that we really need to embrace if we're going to make progress with the shift towards regenerative design and getting closer to the way that biology operates. And with improvements in digital design tools, it should be easier to do this. So one of my colleagues developed a tool that makes it easy to connect up different technologies. So this allows you to put in the resource flows. It shows you anything that is underutilized, and that's a sign that you can add something to the system to create more value. And then you can press play and you can see how it functions. You can see what the flows are. You can even try cutting one of those links, and if the whole system goes into breakdown, then that's a sign that you need to add duplication or redundancy or buffering to make it more resilient. And this allows us to get closer to the highly productive, zero waste, solar powered ways in which natural systems work. And alongside twiddling with all the sort of technical knobs, trying to refine that, we made a note of what was happening to the biodiversity. So this infographic shows what we achieved. So we made a note of birds, mammals, and insects. So literally the same day that the first plants came to site, we had the first birds. Very shortly after that, we had the first insects, grasshoppers, crickets, and then a month later, we had the first butterflies. And bear in mind, this was a long way from the nearest significant patch of planting. As the plants got more established, we had other types of birds, more insects. Then we had a bit of a problem with rats, but we were still getting more birds and insects. Then we had mice to deal with as well, but still more birds and insects. 3 days after the algae ponds were filled, we had the first dragonflies. Where they came from, I don't know. And then we had a feral cat, which is quite handy because the number of rats and mice started going down. More birds, including some quite rare ones, more wagtails, rufous-tailed shrikes, more insects, and eventually we had the first indigenous mammal. It's called a jerboa. So it's like a little hopping kangaroo. It leaves very distinctive tracks. And what I think that shows is that nature does have an amazing capacity to recover if you can create the right conditions. And it's going to be so much easier to make progress if we can do this with nature rather than to it or for it or whatever. And this image shows just how much difference just one pair of beavers can make to a landscape that was largely ravaged by forest fires. But where the beavers have intervened, it's still an abundant system. And to finish, I just want to say a few words about this amazing organism. So this is called a glass sponge. It lives in quite deep ocean water, and it has evolved to make this beautiful lattice structure, incredibly efficient, and it's made that entirely out of locally available materials, calcium, silica, and so on, assembled at ambient temperature and pressure. And what's more, those fibers, they're actually glass fibers with higher optical quality than human-made glass fibers. And each of those goes down into the seabed, and it terminates in a cluster of lenses. That's the image on the bottom right. Those lenses gather light from bioluminescent bacteria in the seabed, and it conducts that light up the organism to put on a kind of lighting display that draws food to the organism. And this, I think, shows the kind of things that we ought to be learning from nature. How to make materials with an absolute fraction of the resource input using local resources, how to make stunningly beautiful, efficient structures, how to foster symbiotic relationships. And above all, I think this points to a new relationship with the rest of the living world. And rather than seeing nature as something separate from us and as something to be plundered for resources, we can see it as a source of wonder and as a source of some of the best solutions to help us make progress in ultimately getting to that point where we are participating as nature and co-evolving as nature. Thank you very much.